Have you ever actually thought about what happens when you press the gas pedal in your car? Or, even when you just flex your arm to pick up your morning coffee? Well, without even realizing it, every single action you take makes you the master controller of a highly complex, dynamic system. Welcome to this explainer. Today, we're going to literally break open the black box of physical reality. We're doing a complete structural analysis of how the world actually works, how it behaves, and most importantly, how we can control it. Okay, let's dive right into our roadmap. We'll be covering 1. What is a system? 2. The dynamic black box. 3. Inputs and outputs. 4. The art of control. And finally, 5. Modeling the world. Let's get to it.
Section 1. What is a system? Let's define the concept. So, when you think about the absolute sheer chaos of the physical universe, how do you engineers even begin to tame it enough to study it? Well, the answer is by defining a system. Strictly speaking, a system is just an operator that transforms physical input variables into physical output variables. But the really fascinating part of this definition is actually in the parentheses. A system is an arbitrary selection of physical reality. To make sense of the world, we basically draw an imaginary boundary around a specific chunk of it. We isolate it, and then we study how the things going into it magically turn into the things coming out of it.
This foundational concept is wonderfully simple. We choose to view this isolated chunk of reality as a classic black box. On the incoming side, you've got your inputs going in. Inside the box, or the système, as our French source material calls it, some sort of transformation happens. And then, on the other side, your outputs emerge. This whole input-output vision is incredibly powerful precisely because it's just so straightforward. But of course, reality is rarely just a static, instantaneous exchange, right? Which brings us to Section 2, the dynamic black box and internal evolution. Out in the real world, things take time. Actions have ripples. A system doesn't just instantly transform an input into an output. It actually has its own internal life. By defining our system as dynamic, we're acknowledging that it involves an internal evolution over time. The inputs trigger some activity inside the box, which unfolds, evolves, and then generates the outputs. Let's make this super concrete with a really fantastic analogy from the source material, a mechanical clock. The winding key is your input. But turning that key doesn't magically and instantly teleport the hands of the clock to a new position. No way. Winding the key powers up an intricate internal mechanism. The gears, the springs. That internal mechanism dictates the dynamic evolution, which ultimately results in the moving hands, which is your output. The real magic happens right there in the dynamics.
Section 3. Inputs, outputs, and perturbations. Categorizing our variables.
Now, to truly dissect the anatomy of these systems, we've got to get specific about what goes into the box because, not all inputs are created equal. We divide them into 2 very distinct flavors. First up, we have commands. These are the inputs we have direct access to, the ones we can actively shape and manipulate to modify the system's behavior however we want. But then we have perturbations. These are kind of the villainous disruptions of the engineering world. They're inputs we don't control, often don't even know are coming, and they absolutely mess with our desired outcome. And the outputs coming out of the box? Those are also divided into 2 categories. First are the functional variables. These are the true, actual representations of the system that we care about, the underlying reality of what's really happening. Second, we have measured variables. This is simply what our sensors can actually see and record. Now, sometimes they're exactly the same thing, but honestly, a lot of the time what we measure is just a limited shadow of the true functional reality. Let's see how this all builds together into a real-world scenario. Think of a car as a dynamic system. When you drive, the steering wheel and the pedals are your commands. You control those. But a massive gust of wind or a patch of black ice on the road, those are perturbations. Now, on the output side, the true functional variables are your car's exact physical position in space and its acceleration. But what does your dashboard actually tell you? Your speedometer just gives you a measured variable, speed. You definitely don't have a sensor perfectly tracking every single functional metric. And hey, this isn't just about machines either. Your own body is a total masterpiece of dynamic systems. Take a muscle, for instance. The input is an electrical command sent straight from your brain. That command triggers a massive, highly complex biochemical dynamic evolution inside your muscle fibers. The output? Mechanical force. Literally, right now, you are constantly sending electrical commands, fighting physical perturbations just to generate mechanical outputs. Section 4, the art of control, taming the system.
So now that we've mapped out the anatomy of the black box, how do we actually tame it? How do we make the system do exactly what we want? Our French source material uses a really great word for this, asservissement. Basically, the ultimate goal of control theory is to analyze the system's natural limits so we can synthesize a rule, a fundamental law of control. We want to force the system's output to strictly follow our command, completely rejecting and ignoring all those unwanted perturbations. We want the car to stay dead center in its lane, despite the wind and the ice.
But wait a second. Before we can design a system to perfectly follow our commands and just ignore the ice and wind, we hit a massive roadblock. How do we actually predict what this complex, dynamic black box is going to do before we build the control mechanisms? I mean, how do we see the future? That leads us to Section 5, modeling the physical world, translating empirical reality to math. To predict the future of our system, we have to translate our messy reality into the clean, rigorous language of mathematics. But as we do this, we absolutely have to remember this crucial quote from the text. A model is only an abstract mathematical description. It can never represent the full richness of the real system. That's a pretty humbling realization for any engineer or scientist, right? Our equations are immensely powerful, for sure, but they are just simplified shadows. They are tools. They are not the full, chaotic reality itself. When we build these mathematical models, we generally have to choose between two paths. First, we have knowledge models. These are built from the ground up using pure physics and physical principles. The variables here have clear physical meaning, but they can get incredibly complex. Alternatively, we have behavioral models. These are completely data-driven. You just observe the inputs and outputs to find math that fits the data, without necessarily understanding the underlying physics. They're definitely simpler, but they completely lack that deep physical meaning. For the scope of the material we're exploring in this explainer, we are planting our flag firmly on the side of physics. Moving forward, our focus will be exclusively on knowledge models. We really want to understand the foundational principles, the actual phenomenological rules governing the gears inside our dynamic clock. And that brings us to the end of our structural analysis for today. But I want to leave you with one final provocative thought. We've seen that we're constantly trying to control dynamic systems using models. But if our mathematical models are only shadows and can literally never capture the full richness of reality, are we ever truly in perfect control? It's that fascinating gap between textbook equations and the unpredictable real world, a gap where the true art of engineering lives. Thank you so much for joining me on this explainer, and keep questioning the systems around you.